Okay, so the first example is we're going to find the general solution, okay, of the following differential equation. Okay, so this is a second order, right? The highest derivative is 2. It's homogeneous because the right-hand side, right, is equal to 0. So again, here we want to, the key here is using the characteristic equation. Characteristic equation, right? The one that's very similar to the quadratic equation, or it is the quadratic equation. Okay, so our characteristic equation in general, okay, is going to be r squared, where r is the root, plus br plus c equals 0. Okay. And I want you to notice the substitutions here that are going on. We have y, well, the second derivative of y, and we have r squared. Okay, our 2 is our a, but our a is general. We have y prime, and we have r. Okay, so we have some derivatives here. So second derivative, second power. First derivative, right, that's really the first power. No derivative, okay, so there's no r here. So I want you to note, okay, what we're really doing here is we're saying y prime is equal to r squared, y prime is equal to r, okay, and then we do our we fill in our substitutions. So let's go ahead and, again, the key is just rewriting this. So this is going to be 2r squared minus 7r plus 3 equals 0. Okay, again, that used to be y double prime, that used to be y. There's no derivative here, so that's it. So this is a wonderful quadratic polynomial, right? It's a parabola, right? It has some vertex. We don't have to graph it. You can for fun. It'll be helpful later on. But we want to find the roots to this differential equation. And again, the directions, right, the instructions are very important. What do they want? They want the general solution. Okay, so we want this general solution. Well, what does that solution look like? Well, it actually depends on what your roots are going to be. I mean, are they going to be distinct? Are they going to maybe repeat? So I'm looking at, so when they want, whoops, general, when they ask for the general solution, right, of a differential equation in this section, you have to ask yourself, is it going to be theorem 5 or is it going to be theorem 6? Now, if you look at theorem 5 in your book, right, it says the roots R1 and R2 of, right, your characteristic equation, of course, are real, right? We're not working with imaginary numbers, and distinct. And the solution, right, which is what we're looking for, it's a general one, so C1 and C2 are coefficients, e to the R1x plus C2 e to the R2x. Okay, so is my solution going to look like this? Or is my solution, going to look like theorem 6, which if I just write it out, it's going to be y of x equals the sum of C1, C2 times x, and we have our exponential function, e raised to the R1x. That's if R1 and R2 are equal. Okay, so if you get a double root. Okay, so again, you have to pay attention to what the goal is. We want a general solution. Again, it's either going to be this or this. Okay, so we go back to our quadratic equation. And I'm going to just write it again since I crossed it out just above. And again, this is just really algebra. Can we factor this polynomial? Well, we definitely can't factor a greatest common factor, right, other than 1. So, right, we go back to our college algebra days, or algebra 2 in high school maybe, and we factor this polynomial, right? And again, all we're doing is really, we're unfoiling this. That's what factoring is unfoiling. So 2r times r, right, is 2r squared. And then again, this is, you could do it by trial and error, or if you want to do factor by grouping, it's any technique that you've learned is fine. As long as you can factor it, that's fine with me. 1 times 3 is 3, right? One of the tricks, right? Inner, outer. 1 times r is 1r. 2r times 3 is 6r. And will I ever get a negative 7r? Well, yeah, if both of these are negative, so I know I'm going to insert these negatives. And again, if you want to FOIL to check, please feel free. I mean, if you FOIL this guy, these factors, you will get this polynomial. And if you need some review in factoring, use any open-ended resource, go online, go on YouTube, any any channel you want, and just put factoring polynomials, and you'll get a great review if you need that. If not, then that's fine as well. Okay, so I factored my polynomials, so whoops, using the zero factor property. So this problem is taking a little bit long. It's not supposed to take this long, but again, it's the first example, so I want to explain really my thought process. So we have either this factor is equal to 0 or this factor is equal to 0. Again, this is all from algebra. And if we solve for r, right, r is just a half. Okay, so that's one of my roots, or they call it sometimes zeros. And I mean, you can call this r sub 1 if you want, since it's the first one. Obviously here r has to be 3. And if you want to call that r2, right, doesn't matter which one you call r1 and r2, just be consistent. And I mean, these roots are obviously, right, these guys, they're obviously distinct, right? They're different roots. They're not exactly the same. So I know that my general solution is going to look like this, because in Theorem 5, it specifically said, well, Theorem 5 says distinct real roots. So we're pretty much done. I'm just going to go ahead and write the solution.